Students, welcome to the fifth session of our first module in compressible fluid flow. Students, today we are going to learn a new concept called stagnation condition. Or stagnation concept of stagnation condition. Okay. So, what is stagnation? I will write stagnation condition. So that is what we are going to learn. So it is a condition called, it also called total condition, also known as total condition. Okay. So here it is defined as a reference state. It is defined as a reference state for a flowing fluid. Okay. The stagnation state of a flowing fluid is defined as the state attained by the flowing fluid when it is decelerated to zero velocity isentropically. Okay. I will write, okay, state attained by flowing fluid when it is decelerated to zero velocity equal to zero isentropically means delta s equal to 0 isentropically. So this is the definition for stagnation state. Okay, stagnation state. Students, I will show you the figure. Okay, suppose this is a flow channel or a tube where flow of fluid takes place. Okay, suppose the fluid is flowing with a velocity v, pressure p, temperature T, density rho, enthalpy H. Okay. Suppose at this section, I am decelerating this fluid flow to a velocity v equal to 0. So the corresponding state or condition is known as stagnation property at the section 1. So here, if this is section 1, the corresponding pressure at section 1 when velocity is 0 is known as stagnation pressure. It must be denoted. Okay, suppose at this section I can write corresponding stagnation properties are P0, T0, rho 0, H0. So enthalpy H0, whenever you use the subscript 0, it means the stagnation condition, the properties or the stagnation properties at that corresponding section. Okay, you use the subscript 0. Okay, so what is I am doing here? I am decelerating the fluid to a velocity equal to 0. So students, the stagnation state of a fluid flow is defined as the state attained by the flowing fluid when it is decelerated to zero velocity isentropically. Oh, that is also very important. Here, delta S equal to 0. So you decelerate the fluid flow isentropically to velocity 0. Then the corresponding state is known as stagnation state. And the properties at that stagnation states are stagnation pressure, stagnation temperature, stagnation density, stagnation enthalpy. And whenever you write those properties, you should use the subscript 0. Okay, use the subscript 0. Then it means they are stagnation properties. Okay. So alternatively, it can be defined as it can also be defined such that as the static state from which a fluid must be accelerated isentropically in order to attain the actual state. Okay, so I can also define that stagnation state is that state from which you can accelerate isentropically to get the actual state, or you can define in opposite way the state that from accelerate from actual state when you decelerate to velocity equal to 0, the obtained state is stagnation. Or stagnation state can also be defined in the opposite way. How? It is the state from which if you accelerate isentropically you get the actual state. Okay, so so this is how this is how we define what how you define stagnation property. The students, I will draw once more. Suppose I am taking a section here, 1, section here 2, 1 2. Suppose the velocity here is v1, pressure p1, temperature T1, enthalpy H1, here V2, P2, T2, H2. When I decelerate the flow isentropically at this position, at section 1, you will get corresponding stagnation state as V will be 0, P01, T01, H01. Similarly, if you decelerate from this point, this section 2, you will get V equal to 0, but pressure, stagnation pressure will be P02, T02, H02. So that is why these are called some reference state. So it varies with the section we are considering. So P01 may not be equal to P02. T01 may not be equal to T02. These stagnation properties or state corresponds to the actual state at the corresponding section. Okay. So the reference state is independent of the type and nature of actual flow that is occurring. If the actual flow, this actual flow, there may be Q, there may be W. Okay. So this reference state is based on isentropical deceleration. Okay. But at every point along the actual flow path, so that is important. So I have taken here two sections. The important point is at every point along the actual flow path, there is a local stagnation state. So corresponding to 1, there is corresponding to P1, T1, H1, there is stagnation properties such as P01, T01, H01. Corresponding to 2, V2, P2, T2, we have P02, T02, S02. So but at every point along the actual flow path, there is a local stagnation state that can be obtained by imaginary deceleration process. Okay. So thus the stagnation conditions are point functions that may be defined at every point in flow process. So every point, at any point you can define a stagnation condition. So students, you have to make sure that this is just a reference state for study. Reference state. These are reference state for what? For the sake of study. So actually at any point in the flow path you can have this reference state. How this reference state are obtained by imaginary actually deceleration isentropically. Deceleration at S equal to constant, entropy constant. Actually this process is imaginary. So imaginary process. So actually in the flow path the fluid is not going to be decelerated to velocity 0, but for the sake of study, we are imagining if we decelerate the flow at a particular section to 0, what will be the condition of the fluid. So that properties and what will be the properties corresponding to that particular stagnation condition. So that is our that is just for sake of study. So we are defining such a reference state. Okay. So it is not actually taking place in that. You should be very clear that we are not at all decelerating the flow at any positions in the flow path, but we are considering we are for the sake of study we consider what will happen if the flow would have been decelerated to zero velocity isentropically. What will be the properties? So that imaginary process refers to the stagnation condition. Okay, so I can show this in HS diagram, enthalpy entropy diagram. So this is section 1, so this is section 2. Okay, corresponding to section 1, H1 H2 are the enthalpy, P1 P2 are the pressure. Okay, so I am marking this H1 here. So this is H1, this is state 2, H2. H1. So corresponding pressure lines are drawn like this. So this is P1, this is P2, and I am isentropically decelerating, means isentropic process will be vertical because here S should remain constant, S1 S2. Okay, here also. So it will reach a position called H. So enthalpy corresponding to this should be H01. Enthalpy corresponding to this should be H02. So this value should be H02, and the pressure line should be, this should be P01, this should be P02. Okay. So this point is 01, this point is 02. So what happened? S1, S2 remain constant. So these are the two stagnation properties. Okay. Now I will show some relationship between suppose the stagnation enthalpy out stagnation enthalpy. We know the SFFE equation, right? SFFE equation. What is SFFE equation? H1 plus V1 square by 2 equal to H2 by V2 square by 2, right? If no heat and work transfer occurs, and if Z1 equal to Z2. If there is no heat transfer, there is no shaft work, there is no elevation difference, then energy equation can be written as H1 plus V1 square 2 equal to H2 plus V2 square by 2, right? Suppose we are isentropically decelerating from 1 to 2. 1 to 2 isentropically decelerating from 1 to 0 1. So this is our stagnation, this is our actual condition. actual condition to stagnation condition, we are isentropically decelerating to v equal to 0. So then what will happen? What will happen? h1 plus v1 square by 2 will become h01, right? h01 plus v2, the velocity will be 0. So therefore we can write therefore we can write therefore we can write h we can write h01 will be equal to h1 plus v1 square by 2. So this is the relationship between stagnation enthalpy and actual enthalpy. Okay, the stagnation enthalpy at any location in the flow field is sum of static enthalpy and kinetic energy possessed by the fluid at that location. Now stagnation temperature. Since we have written h0 equal to h1 plus v1 square by 2, I can write h0 is nothing but cp into t0 plus h1 is cp into t1 plus v1 square by 2. So this gives t0 equal to t1, sorry, you write it as h and h0, okay, or h1 and h01, or h2 and h02. So I'm not using the subscript 1 here. Generally h plus v1 square h I'm rubbing this 1. Okay, yes. Okay, now t0 will be t plus v square by 2 cp. So that is the relationship between static temperature and stagnation temperature. Okay, so this is the relationship between h0 equal to h plus v square by 2. So if I rub this 1 off, this will be a general equation. Okay, so h0 equal to h plus v square by 2. Similarly, t0 equal to t plus v square by 2 cp. V square by 2 cp. Okay. Now, oh, I can write t0 equal to t plus v square by 2 cp, right? So since cp equal to gamma by gamma minus 1 into r, do you remember this equation? The relationship between cp, actually cp by cv equal to gamma, cp minus cv equal to r. There are this equation, when you combine these two equations, you will get cp equal to gamma by gamma minus 1 into r. Okay, now I'm writing t0 equal to t plus v square by 2 cp, right? Instead of cp I am writing gamma by gamma minus 1 into r. So what will happen? So I am taking gamma minus 1 to numerator, t plus gamma minus 1 by 2 v square by gamma r, right? So if I am taking t common, so it will become here 1, here t. So what happened? I took the t outside the bracket. So this came inside the bracket. So students, what is this term? Do you remember? In case of perfect case, what is gamma RT? You learned a equal to root of gamma rt, right? Therefore a square will be gamma rt, right? Right? So I am substituting this equation as t0 equal to t into 1 plus gamma minus 1 by 2 v square by a square, right? So what is v by a? V by a is nothing but Mach number. Therefore t0 equal to t 1 plus gamma minus 1 by 2 Mach square, right? Or I can take this t to the left hand side. So t0 by t equal to 1 plus gamma minus 1 by 1 plus gamma minus 1 by 2 into Mach square. Okay. So students, you know this process from t to t0 is isentropic deceleration, right? So for isentropic deceleration, since this process is isentropic deceleration, you can write t0 by t should be equal to p0 by p into gamma by gamma minus 1. This is ideal. Delta is equal, since delta is equal to 0, this is adiabatic or isentropic process. For adiabatic or isentropic process, you can write like this, right? Sorry, actually this is should write like gamma minus 1 by gamma. Okay, gamma minus 1 by gamma. So p0 by p will be equal to t0 by t all raised to gamma by gamma minus 1. But already you know t0 by t is nothing but t0 by t is nothing but 1 plus gamma minus 1 by 2 into Mach square, right? So you can substitute it with 1 plus gamma minus 1 by 2 Mach square into gamma by gamma minus 1. So this is the relationship between P0 and P. P0 and P. Stagnation pressure and static pressure. Similarly, you can write rho 0 for adiabatic or isentropic process. Rho 0 by rho is nothing but T0 by T all raised to 1 by gamma minus 1. Therefore, rho 0 by rho will be equal to 1 plus gamma minus 1 by 2 Mach square 1 by gamma minus 1. So this is the relationship between density, stagnation density and static density. So this is how we write the relationship between different properties of stagnation state. Okay. So the velocity, the velocity of sound at stagnation state is A0. A0 will be equal to corresponding to gamma R into T0. T0 is the temperature at stagnation. Okay. Now we have to calculate the entropy change in terms of stagnation state. Okay. So I am drawing the HS diagram here, entropy diagram. HS from 1 to 2. So this pressure is P1, this pressure line is P2. Okay. So from here isentropical to some 0 1 position here to 0 2. Okay. So this pressure is P01, stagnation pressure corresponding to 1. This pressure is P02 and this is 02. Okay, wait. Suppose I'm changing this the T. Let this be TS diagram, okay. So this temperature will be T01, this temperature will be T02, T1, T2, okay. So what is the process? Process is taking place 1 to 2. So actual process is some process from 1 to 2, okay. So this is the process from 1 to 2. So these are the stagnation points corresponding to 1 and 2. So students, actually entropy change is nothing but delta S equal to, suppose this is S1, this is S2, delta S is equal to S2 minus S1. S2 minus S1 means this distance, S2 minus S1, okay. Now, the general equation for delta is equal to S2 minus S1 can be written as Cp log. You might have learned in thermodynamics, Cp log T2 by T1 minus R log P2 by P1. So this is the general equation. Okay. Suppose I am writing Cp as gamma by gamma minus 1 R log T2 by T1 minus R log P2 by P1. And if I take gamma by gamma minus 1 inside the log, it will become R log T2 by T1 gamma by gamma minus 1 minus R log P2 by P1, right? So R can be taken outside. R can be, delta is equal to R can be taken outside to get what, log T2 by T1 gamma by gamma minus 1 minus log P2 by P1. R is taken outside. Since log A minus log B is nothing but log A by B. So it will become R log T2 by T1 gamma by gamma minus 1 by P2 by P1. So this equation will become in this way. So students, I am taking this numerator. Wait, I will show you. T2 by T1 can be written as T2 by T01 into T01 by T02 into T02 by T1, right? Sorry. Better to write T02 T2 by T02 into T02 by T01 into T01 by T1. This can be written right because T02 T02 cancel, T0 by T01 cancel, remaining is T2 by T1. So T2 by T1 can be written this way, right? So if you add gamma, what is gamma by gamma minus 1 here, means you should multiply by gamma by gamma minus 1 gamma by gamma minus 1. The whole divided by, if you add P2 by P1, means you whole divide by P2 by P02 into P02 by P01 into P01 by P1, right? So this means you get if you multiply this, you will get P2 by P1 only, right? So students, what will be but you know the value of the equation, you will get here. Okay, T0 by T equal to P0 by P gamma minus 1 by gamma, or the other way, what you take it to this side, you will get gamma by gamma minus 1 equal to P0 by P, right? P0 by P. Okay, this you know. So here this term and this term are equal, right? Similarly, this term and this term are equal, since this follows adiabatic equation. P01 by P equal to T01 by T1 gamma by gamma minus 1. Okay. So this term and this term cancel, this term and this term cancel. So finally what remains? Finally, remaining thing will be T2 by T1 all raised to gamma minus 1 by gamma by P2 by P1 equal to T02 by T01 all raised to gamma minus 1 by gamma. Sorry, not gamma minus 1 by gamma. Gamma by gamma minus 1. Gamma by gamma minus 1 will be equal to P02 by P01. So students, I am substituting this equation in over. I am substituting this equation here. T2 by T1 always to gamma by gamma minus 1 equal to P2 by P1. This equation for delta S. Okay. So for delta S equal to R log T02 by T01 all raised to gamma by gamma minus 1 by P02 P01. Okay. So this is the relationship between the entropy change in case of stagnation properties. Okay, this is the relationship between entropy change in case of. So if T02 and T01 is same, if T02 equal to T01, then T02 equal to T01, then delta S equal to minus R log 1 by P02 by P01, right? Or you can write minus R log P02 by P01. So when T02, the stagnation temperatures are same, then the equation will become delta S equal to minus R log P02 by P1. So this is how we write the entropy relation. So this is how we write entropy relations. So students, now we will learn the concept called kinetic form of SFEE, steady flow energy equation. You know the steady flow energy equations, H plus V square by 2 equal to constant, or that constant will be equal to H0, right? Stagnation enthalpy, right? Now this can be written as CPT plus V square by 2 equal to CPT0, right? Now I am substituting for this Cp with Cp equal to gamma by gamma minus 1 into r, right? So gamma by gamma minus 1 into r t plus v square by 2 will be equal to gamma by gamma minus 1 into r t0, right? So what is this gamma rt? That gamma rt and gamma rt0, that will be a square by gamma minus 1 plus v square by 2 equal to a0 square by gamma minus 1. Okay, so this form is nothing but kinetic form, because here only velocity terms are here, only velocity velocity of sound and flow. So that is why this form of energy equation is known as kinetic form of steady flow energy equation. So all the three terms are kinetic energy equation, right? So the suppose suppose I'm coming to another form, another type called adiabatic energy equation. So suppose the maximum kinetic energy and maximum velocity associated with an adiabatic flow would occur when, if we imagine that all the thermal energy of the flow is converted into kinetic energy, right? Like if our equation was a square, kinetic form was a square by gamma minus 1 plus v square by 2 equal to a0 square by gamma minus 1 or equal to some constant. So a0 square by gamma minus 1 will be a constant value, because a0 is constant. A0 won't change, stagnation condition, but corresponding to a particular state is constant. A and B changes, but A0 corresponding to A never changes. So A0 square by gamma minus 1 equal to a constant. Suppose I am extracting all of the thermal energy to convert into kinetic energy. So what will happen? When the whole thermal energy is extracted, the temperature of the fluid becomes 0. If whole thermal energy extracted, what will happen? What will happen to the temperature of the fluid? Temperature will become 0, but velocity of the sound is in the medium will be, what will happen if temperature becomes 0? Students, I'm asking, if whole of the thermal energy from the fluid flow is extracted, if whole of the then what will happen? Temperature will be equal to 0, right? If temperature is equal to 0 means gives a equal to 0, because a is nothing but root of gamma rt. So if t becomes 0, a will also become 0, right? If a becomes 0, what will happen? A square by gamma minus 1 plus v square by 2 equal to some constant, right? So if a equal to 0, v will become maximum. V will become Vmax, maximum velocity possible. So this will become, if you put here 0, this constant will be equal to, V will become Vmax, right? Vmax square by 2 will become the constant. Okay, the constant will be equal to Vmax square by 2. So therefore you can write a square. So a square by gamma minus 1 plus v square by 2. V square by 2 is nothing but a0 square by gamma minus 1, also equal to a constant, also equal to what? Vmax square by 2. Vmax square by 2. So that is the maximum possible. Vmax is the maximum possible velocity if a is 0. So these are various equal terms. Now another case. So consider a section where the flow Mach number is equal to unity. if Mach equal to unity means V equal to A. V equal to A. So such a section is called such a section. Such a section where m equal to 0, m equal to 1 is critical section. It's known as critical section. So let the values of the properties at critical section be superscripted by star. So P star, T star, rho star. So these are star corresponding to critical section. Critical section is those section with where Mach number is 1 or velocity of flow is equal to velocity of sound, right? So a square by gamma minus 1 plus v square by 2 is constant, right? So it can be written as another form is a1 square by gamma minus 1 plus v1 square by 2 equal to a2 square by gamma minus 1 plus v2 square by 2, right? v2 square by 2. Or suppose the second section is the critical section. If the second section is critical section, you can write suppose first section you are not using the subscript 1, you will just write a square by gamma minus 1 plus v square by 2 will be equal to second section is critical section means a star square by gamma minus 1 plus v star square by gamma minus v star square by 2 will be equal, both the value will be equal to some constant, the same constant, right? But a star is equal to v star because these are star value in critical section. At critical section is at critical section because Mach is 1, right? Mach is 1. Therefore I am substituting here with v star with a star. Okay, then what will be the equation? A square by gamma minus 1 plus v square by 2 equal to a star square by gamma minus 1 plus a star square by 2 because a star is equal to v star, and this will become 2 a star square plus gamma minus 1 a star square by 2 gamma minus 1, right? So you will get a star gamma a star square plus 2 minus, okay, and this if you simplify it you will get, a square by gamma minus 1 plus b square by 2 is equal to gamma plus 1 a star square by 2 gamma minus 1. This will be equal to a constant. So this is another term. So in general, right hand side is same, left hand side is same, right hand side varies. So what can you write? A square by gamma minus 1 plus v square by 2 equal to v max equal to, you can initially we wrote a0 square by gamma minus 1, right? This is also a constant. It is also v max square by 2, right? Now we have also written one more term. What? Gamma plus 1 by 2 gamma minus 1 a star square. Okay. So this is the adiabatic steady flow energy equation incorporating the three speeds a0, vmax, a star. So this is the relationship between a0, a star, vmax, all the different vmax. The maximum velocity that can be obtained by the fluid flow when thermal energy is extracted to thermal energy is completely extracted, that is Vmax. A star is the velocity of sound at critical section. A0 is the velocity of the velocity of sound at stagnation property. So this is the relationship between all these three reference velocities. All these three reference velocities are um, reference velocities are related in this way. So this equation is adiabatic energy equation. Adiabatic energy equation. Okay. Full form of adiabatic energy equation. So I will write full form of adiabatic energy equation. Okay, students. So students, now we are going to learn another concept called Prandtl velocity ellipse or adiabatic steady flow ellipse. So from the previous equation we have learned with our, so in the previous relation, so here this term is nothing but an equation, a form of ellipse, right? So this is in the form of ellipse where our variable. So generally x square plus some a plus y square plus b equal to 1 is our is the form of is the equation for ellipse, right? Is the equation for ellipse. So where x and y are the variable or the major x and y are the variables, right? Now in this equation, this is a similar form of equation for ellipse, right? So this equation can be plotted as ellipse. So since only positive values of a and b are practically possible, here our variables are a and v. Okay, a and v. Instead of x and y, our variables are a and v. Only positive values are only possible, practically possible for sound, right? So x and y can be negative, but a and b cannot be negative because they are velocities. Velocity can never be, magnitude of velocity can never be negative. So for that equation, the first quadrant ellipse is only possible. First quadrant ellipse. So the ellipse will be in this way. Okay, this is a, this is velocity. Ellipse will be in this form only. A first quadrant ellipse is only possible because a and b can only be positive values. If a and b can be negative, the complete ellipse is possible. But since a and b are only positive, first quadrant ellipse is only possible. So this ellipse is known as Prandtl velocity ellipse or adiabatic velocity ellipse. Suppose when a equal to 1, suppose this line is m equal to 1 or v equal to a. At this line, anywhere v will be equal to, if this is v1, this is a1, in this line v1 will be equal to a1. Suppose this is v2, this is a2, here v2 will be equal to a2 in this line. So this line is nothing but line of Mach equal to 1. Okay. So this line is Mach equal to 1. Now we can this ellipse is an useful device for examining the relationship between flow velocity and speed of sound. So this ellipse is drawn with gamma equal to 1.4. Okay, if you give the value gamma equal to 1.4, you can determine phi. So some this region can be divided into 5 regions, this region and this region. So first region is nothing but here velocity is almost 0 or a is very high compared to In the first region, V is very less than A. V is almost 0. Such region is nothing but incompressible region. Regimes close to the this axis, y-axis is V very less than A, incompressible. This will be subsonic. This will be transonic. So this will be supersonic. This will be hypersonic. Okay. So this is how Prandtl velocity ellipse is. So this Prandtl velocity ellipse is a first quadrant ellipse. This ellipse can be divided into 5 regions. The region close to Mach number 1 is transonic region. So this particular is sonic because V is equal to A. Region close to M equal to 1 is transonic, and this will be supersonic because towards this axis V becomes very higher than here. V will be very higher than A. Here V will be very lower than A. So this will be incompressible, this will be hypersonic. Okay, this is how. So we have already learned the range of values. Actually, in case of here Mach number will be less than 0.3, right? Here Mach number will be some 0.3 to 0.8, right? Here 0.8 to 1.2, here 1.225, right? So such a range you have already learned. Greater than 5 is hypersonic. Okay. So hope you have understood the concept of Prandtl velocity ellipse. For the time being, we will stop this session. Thank you.